All right, so this lesson is on curvature. Now, curvature is a number that represents how quickly a curve is changing direction at a certain point. Um, so the bigger the number, the more curvy the thing is, essentially. Now, it's given the Greek letter kappa, and very informally, you can kind of think of it like right here. You can kind of tell that that curve is pretty curvy there and pretty not curvy here. So the curvature is greater at this first spot than at this second spot. Um, Now, the way you measure it is you measure it in terms of how quickly the unit tangent vector is changing. So right here, like if we're going around the curve this way, you can kind of tell that the unit tangent as you go around is changing pretty quickly as you move in steady units around that curve. And then eventually right along here, they barely change at all, right? So here the curvature is pretty light because that unit tangent doesn't change much. Here it changes pretty significantly, so it's considered a high curvature there. So a lot of students think that this should be represented. You're measuring how fast the unit tangent is changing as you move around the curve. A lot of students think that should be t prime of t. But that's not actually the case because little t, if you think of it as like a time parameter, there's nothing that says you're moving at a constant velocity around this thing. So maybe at one point you're here, at one time you're here, the next time you're there, like 1 second later you're there, 1 second later you're here, 1 second later you're there. So that means that your unit tangent might change significantly in a short period of time, but it's not really being measured according to a steady pace around the curve. That's what you want to measure, is moving steadily around the curve. So in order to take care of that, you're looking at the derivative with respect to arc length. Okay, so you have a starting point, and then as you move according to a specific set of units for the arc length, you can measure how quickly that tangent line changes, that unit tangent changes. And then, so the derivative wouldn't be a scalar. So what they do is they take the length of that, because it's actually a vector. Okay. So anyway, this is the formal definition of curvature. It's defined in terms of arc length S. Okay. So let me get rid of this down here. And now it turns out there are two other formulas. So this one's the definition of curvature. There are two other definitions, and so this requires you to know what T of S is, because we're looking at T prime in terms of S. Normally, you have T in terms of T and R in terms of T. So what people have figured out are other convenient formulas you can use. In this case, you would only need R, and in this case, you'd need T and R. Okay? So what we'll do is we're going to show that you can take the definition and turn them into these two formulas, these two other versions in terms of T, little t. Okay? Now, it's complicated, but it uses a lot of pretty good math in there, so that's why we're going to do this. So first, let's write down the definition again. So kappa, or curvature, equals the magnitude of the rate of change of the unit tangent with respect to arc length. Okay, which is the same thing as T prime of S. Okay, and recall S is the arc length function, and T is the unit tangent function. Okay, so really what we want is K in terms of T. Well, if S is in terms of little t, so if we have little s in terms of little t, remember parameterizing arc length with parameterizing in terms of arc length as opposed to in terms of t. We needed to figure out s in terms of t, because then we could plugged that in and rearranged our original R of t into R of s. So if we have S of t, then you could think of t of s as t of s of t. So then that means that t prime of t, this is really like a t of t, right? T in terms of little t. T prime of t, if you use the chain rule, would be dt little dt, or d little t, which is the same thing as the derivative of the first, the outer function, with respect to the first variable, times ds dt, the derivative of the inside, with respect to the innermost variable. So this right here is the chain rule. Okay. Now, if I rearrange a bit, let's see, do I want to rearrange a bit? Yeah, if I rearrange a bit, then I can get, this right here, by the way, is t prime in terms of s. That's what we want. So I'm going to divide by ds dt. This is s prime of t. And this is this, right? So if I divide both sides by ds dt in this equation, then we get dt dt over ds dt equals dt ds. Okay. And one other thing, remember that s of t is the arc length function. So it's the integral from a to t of the magnitude of r prime of t dt. Okay, so recall this. This is the arc length function. Okay. Well, I'm going to switch that out so that we're using, instead of the t's here, I'm going to switch it out with the dummy variable. So it's still a to t, because that's what the function is based on. That's these t's here, this t and this t. So if I switch it out, it's r prime of u du, and that's s of t. So that means that s prime of t is going to be d dt of the integral from a to t, magnitude r prime of u du, which actually equals just the inside, r prime of u. Why is this true? This is true because of the fundamental theorem of calculus from single variable, which says that d dx, the integral from a to x of f of t dt, equals f of x. Oh, sorry, I made a mistake here. This is r prime of t. Okay, and that's using the fundamental theorem of calculus. So I can go back and tweak what I have up here, because s prime of t is really ds dt. So now I can rewrite this dt ds equals dt dt, whoops, there, over this, the magnitude of r prime of t. Okay, well, the top is t prime of t. Okay, so if I wanted the magnitude, now remember, this is almost the magnitude. This is almost curvature. Curvature is defined as the magnitude of this. So if I throw a magnitude here and a magnitude here, this is my curvature. Well, the magnitude of a magnitude is just the original magnitude. So I don't really need the red line, the red bars to go over the whole thing. I can just turn this into r prime of t inside its own magnitude, and then the top would be this, t prime of t. And so now we've proven this part right there. Okay? So this one, a little more annoying to prove, but we're going to go for it. Okay? So let me highlight this. This is kappa. And there's one of the major outcomes that we got. Okay? So the other way of doing this, we're going to try to prove from, let's see, which one do we want to use here? We want to try to prove using this, the thing in the cloud, that we get the other equation, or the other expression for curvature, this guy. Okay? So, this is not going to be intuitive at all. What I'm going to do first is start with t of t, and then we'll eventually take the derivative and the magnitude and all that stuff. So first let's start with t of t. Okay, we know that's r prime of t over the magnitude of r prime of t. And we know that the magnitude of r prime of t is equal to s prime of t from up here. S prime of t turned into that. Okay? All right. So that means that r prime, let's see, what else do we know? If we rearrange this, we know that r prime of t is going to be t of t times the magnitude of r prime. So r prime of t times t of t, which, let's see, what else do we have? Which is going to equal, using this substitution, s prime of t times t of t. Okay, so let me get a second derivative for r prime in there, because notice in the equation we have a second derivative involved. So the second derivative, r double prime of t, is going to be, and then I'll use the product rule on this thing. So it's the derivative of the first times the second plus the first times the derivative of the second. Make sure I did that right. Yeah, that's right. Okay, now back up here in the equation, I need the cross product of r prime and r double prime. So let's calculate that. R prime of t cross r double prime of t. All right, so I'll write it out first. So r prime of t is s prime of t, capital T of t, and then we're crossing it with s double prime of t, t of t, plus s prime of t, t prime of t. Okay. Ooh. So let's think of this as a vector u. Let me use a different color so it shows up better. So this would be vector u cross the sum of two vectors v plus w. Now we learned, I don't know, back in unit 6 or something like that, one of the properties, the way that this distributes is you get u cross v plus u cross w out of this. So we need u cross v plus u cross w. So down here, this is going to turn into u cross v. So s prime of t, t of t, cross the first one, v here, s double prime of t, t of t, plus, and then we've got the u again, s prime of t, t of t, cross the second one, S prime of t, t prime of t. Okay, so when you're cross-producting, when you're taking the cross-producting is not a word, of things that represent scalars in front of the vectors, then you can actually bring out those scalars in front, and you get S prime t, S double prime t, t of t cross t of t. And I can do the same thing over here and pull out. Now notice each one that you pull out comes out by it sort of, how do I describe this? Each one comes out in front. Each constant comes out in front. It's not like you factor it out of both terms simultaneously. You factor them out one at a time, and that takes care of it. So the S prime factors out once and twice, and so you end up with S double prime, or no, sorry, S prime of t times another S prime of t. And then you get the t of t cross t prime of t. So that's using the rule that if you have C U cross V, that turns into C of U cross V, right? So if there's a CU cross a CV, you actually get C squared U cross V. That's a common misconception that you factor out one C and that's it. Okay, so we have a property here that we can use. Any vector cross itself is the zero vector. So this whole thing, no matter what that is, times the zero vector is going to be the zero vector. And then I'm going to add it to this vector. Okay, so all this turns into S prime of t squared. And then next to it, we've got t of t cross t prime of t. So that's really just the remainder part over here, because the rest of it was the zero vector. Okay, now t of t is a unit vector, remember. So since the magnitude of t of t always equals 1, we have that property that we figured out a while back. If a vector function always has a constant length, and we know that that function and its derivative are, those two vector functions are always orthogonal to each other. So we know t of t dot t prime of t has to be 0. That's related to that sphere problem that we did. So t of t is going to be perpendicular to t prime. Okay. And the idea is that neither of these are the zero vector, otherwise what's the point? Well, in fact, t can't be the zero vector. And if t prime was the zero vector, then we don't have any curvature in the first place. So the curvature would be 0 anyway. So okay. So let's keep going here. All right, let's see. Okay, so now we need the magnitude of this thing. Okay, because remember up here in the formula, it's inside a magnitude. All right, so let's find the magnitude. Magnitude of r prime t cross r double prime t. Okay, so that's going to be the magnitude of s prime of t squared, and then t of t cross t prime of t. All right. Well, this part works as a scalar, so I can pull that out of the magnitude part. And then this is a cross product, but it's the magnitude of a cross product. So you might remember this rule from a way back. U cross V, that's the area of the parallelogram defined by U and V, right? Well, that's the same thing as 2 times the area of a triangle, which is magnitude of U, magnitude of V, sine theta. That would be half of that. This triangle is 1/2 U, V, sine theta, the angle between them. And this would double it, dot, 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 right? So together is just UV sine theta for the area of the parallelogram. So this is U, V, sine theta. Okay, so let's replace the T cross T prime with magnitude of T, magnitude of T prime, sine of the angle between them. But notice the angle between them is 90. So sine of 90 is 1. So this thing is 1. The unit tangent vector is a unit vector, so its length is 1. And so now, right now, all I'm left with is s prime of t squared times the magnitude of t prime of t. Well, s prime of t, remember, where is it? S prime of t is the magnitude of r prime of t. So this thing turns into the magnitude of r prime of t squared times the magnitude of t prime of t. So that's this. All I'm doing is I'm bringing that down now. Okay, well, let me divide both sides by r prime of t squared. So then I get this, r prime of t cross r double prime of t magnituded. That's not really a word, but you get it. Equals the magnitude of r prime of t squared, or over the magnitude squared, equals the magnitude of t prime of t. Okay, now recall that curvature in the formula that we derived before was the magnitude of t prime of t over the magnitude of r prime of t. So that turns into the magnitude, using this substitution for that first term, it's going to be r prime cross r double prime over r prime squared, the magnitude squared, all over another r prime magnitude. Well, if I multiply both the top and the bottom by r prime squared's magnitude, or r prime's magnitude squared, then we get this, r prime of t cross r double prime of t inside the magnitude divided by r prime of t all cubed. Whew. And that's it, right there. Boom. You love it. You know it. All right. Okay, I'll see you guys soon. Take care.